Okay, cool. So yeah, so like I said, section 27, uh, we're gonna talk about our first well, not our first, but like a big machine learning algorithm. In this case, it's gonna be K nearest neighbors, so KNN, and then we'll talk about some evaluation metrics, for example, like accuracy, precision, recall, and then using that stuff to, for example, like confusion matrices. And the stuff that we're doing today, especially for the evaluation metrics, that extends out for the other machine learning algorithms and other techniques that we can use that we'll talk about throughout this module. So kind of just know, like, it's not like, oh, it only applies to KNNs. It actually applies beyond that. Okay. So let me go ahead and start sharing my screen. And why can't I adjust? Okay, cool. So I realize I'm at the wrong place. Okay, so share my screen. And I believe this is right. Okay, so you should see my Jupyter workspace right here, mod 3. Like last time we talked about was time series, right? Talked about time series for a couple sections and modeling and stuff like that. And so today we're going to talk about KNNs. And of course, this is all in the GitHub repo that I usually upload to. So just know that's the same structure there. So the first thing we're going to talk about, get rid of these guys so I don't get confused. We're going to look at KNNs. So let me make sure I'm going to do a restart. Okay, so the first thing we need to talk about for K-nearest neighbors, before we even get to that, is we need to figure out how to measure how far something is, which doesn't actually seem like, I don't know, when I say that, it's like, oh, we need to figure out how far something is. It doesn't seem obvious to be like, well, that's pretty simple. Like you just see like, oh, what the difference is. But we need to formalize that. And the reason why is because there's actually different ways we can identify what is close, what is near us. And that's kind of like what the K-nearest neighbors comes from. So you can think of it like when things are close together, it's kind of like a proxy for how similar they are. So when we talk about this, it's like you can kind of imagine this like, like an analogy wise, like, oh, friends who are close together, who are hanging out closer together, they're probably more similar to each other. When we have data, and you can think of it like two-dimensional data, like if I go ahead and draw some stuff out like this, I'll usually do two-dimensional, but notice it expands out to higher dimensions, 3, 4, 5, and so on. Is that if I have data points, oh, I don't like that color. Let's just use black. So if I have points like this over here on some X, Y, feature, for example, I don't know, like I'm trying to think of a good example, but think of like two different features. Like this is your target. This is like a feature over here, okay? Is that if I have points that are very close together, it's likely that they are similar. So if I have a new point come in and I say, oh, the point's right here, well, it's probably most similar to these ones compared to this group over here because they're so far away. Okay, so that's kind of the idea of like, saying, oh, if things are close together, they're probably similar together. And of course, we can extend this out to 3 dimensions or for, even higher than that. As we get into higher dimensions, that's when things start getting a little tricky. And we'll talk about that issue too. But the concept's there, I think, and that should hopefully make a lot of sense. And that's where basically K-nearest neighbors gets its motivation. But before we can do that, we actually have to say, all right, how do you calculate distance? So I'm going to start off with like actually the simplest kind of distance, which is probably not your intuitive part. So like you probably like can think of like a distance like, oh, in the real world, if I wanted to know from here to here, I would just take like a ruler or, like tape measure and measure it out and say, oh, it's 120 centimeters away, right? Like that's kind of direct. And if it's like at an angle, you just go from here to here, that's 120 centimeters away. So you can always measure this one-dimensional distance, no matter if you're in 2 dimensions or 3 dimensions, or in the case 4, 5, 6, whatever dimensions. Okay, but Manhattan distance is the first one we're going to talk about, and these are all discussed in the curriculum. But I'm just going to show you guys a little bit. This actually directly from the curriculum. This image right here. But the way you can imagine this, like, and we'll start with a 2D because obviously it's easier to see in 2D, is that you can kind of imagine saying how far is this point to here, and you can imagine a grid system and say, okay, well, basically traveling along this grid, we can go to here. So like, we go like 1 unit, 2 units, 3 units, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this is kind of like, oh, it'll take us 12 blocks, you know, or like you can say like 12 steps or something like that to get all the way there. And so you'll notice here there's also this blue and this yellow line. It turns out, if you count this out, it turns out this is the exact same thing. So if I go like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Basically, anytime you use that grid, you'll always get the same number. And this is called the Manhattan distance. And so this is kind of like the most like, I would say like level 0 of distance, to the point where like you probably know better and you probably haven't even thought about this, but like this would be closer to be like if you put into Google Maps, right? And you say, how far is it? Well, you know, this from here to this point over here is more like how far the crow flies, right? You're like, oh, if I just flew all the way over there, that would be the distance. But because I have to actually travel on the streets, this is the actual distance. And it turns out if we have a grid like this, a nice, easy, I don't know, orthogonal, I don't know, that's the best way. But if we have a nice grid like this, is that we can actually say, okay, it's just the distance that we would travel on those streets to get to here. And it's cool is that we don't care about how big the streets are, how big the units are, it will always be the same number. So that's a nice thing for about, I mean, when you're doing a distance, you want to be able to calculate the same way no matter what. So now we can actually put this formula. So first of all, you guys have any questions about this? Hopefully this seems pretty straightforward. Just a way to basically say how many steps would it take versus like what the actual distance away from you. Okay, cool. So there's a formula. So basically this formula, and you'll see like why I'm showing this formula, it'll more generalized, but basically the distance from A to B. So you can imagine this is A right here, this is B over here. And we basically just sum basically those steps that we take from AK minus BK. And that K part, just know that's like a dimension. So like if we have one dimension, okay, it's just saying, well, how far from here? One dimension is just a line, right? So if we had a point right here, it would just be, oh, it's a distance of 1, 2, 3, 4, 5, 6. Okay, and that would be our distance. If it was on 2 dimensions like this, we would say, okay, there's this direction right here is a distance of, 6. And say, okay, the direction in the Y direction, okay, that's also in this case 6. So you'd add those up. So it'd be, okay, 6 plus 6, 12. If we had a 3rd dimension, so if you imagine like, if I took that drawing and it's like, this is A, this is B, I put it downwards and it's like, oh, well, let's say we also like raise it up like 2 units. You would have to figure out the 2-dimensional part and then the 1-dimensional or the 3rd-dimensional part. In that case, it's like, oh, it's 2 steps up. And so you just add that to the distance. Okay, so you can think of it like if you're traveling on to an apartment, in apartments on the 3rd floor. Well, you have to take, let's just say like 30 steps, west, and then like 20 steps north, and then you have to travel up 3 floors. Okay, so that would be kind of like the Manhattan distance in that case. All right. So that's the formula, and you'll see that's absolute value. That way you make sure we don't care about, if you're going left or right, east or west. It doesn't matter. We just care about like how far it is. We don't care about what direction. All right. So in this case, I have a little coding part, and we'll kind of use this a couple times just to kind of show you how it goes through. This is not the curriculum, just to let you know, but I think this one kind of says it out. The curriculum actually uses a for loop, just kind of let you guys know when they're showing these things off. Which is fine for like understanding how you could do this. Like you can say, okay, well, let's go through each dimension and figure each part out. But for loops tend not to be very efficient. It turns out vectorization with NumPy, which remember if we talked about NumPy before, NumPy does a really great job on actually making things a little more efficient, okay, in memory space. So you'll need to see I'm gonna apply NumPy, and you'll notice that it makes a lot of sense when you write it out. So I have 2 different points, A and B, and you'll see that this right here, 2, 3, 5, 1, minus 1, 3, you can think of those on a coordinate plane, of a 3-dimensional coordinate plane. So somewhere in 3 dimensions where, say 2 units, 3 units, 5 units up, another one is like 1 unit, that direction, maybe minus 1, like in the southern direction, and then like up 3. So like that's the idea that we have for this ABC, or for this AB. Okay, and we can see that's our points right here, and these are just NumPy arrays, so I can actually do vectorization on it. Okay, and so I can just simply say, okay, what's the differences? This A minus KB. So if I did this in a for loop, I would have to go through each dimension and go, okay, the first dimension, do A minus B, at least the first part. So it'd be like 2 minus 1. And then I have to go to the next one, go 3 minus 1, and then do all those up parts. But instead with vectorization, I can just do it all at once. So this is a vector right here. This is a vector here. I can subtract those two, and you get one resulting vector of those differences. 2 minus 1, 3 minus 1, or 3 minus -1, 5 minus 3, and you can see I get that result. Okay, follow me so far? Sound pretty good? Cool. All right, stop me if I'm not, if it's confusing. Now I'm taking those differences that I saved up here. I could have done this all at once, but I'm kind of spreading it out. And I say, okay, let's take the absolute value with NumPy. Okay, and what's nice is that NumPy basically will broadcast it over and say, all right, let me go ahead and apply it to every part. In this case, we'll just get the same thing since it's just all positive. But this would work if it was like -4, make it +4. So a +4 distance. And then all we got to do is just add these up. So 1, 4, 2, that should be 7, right? And we run this, and you can see we get 7. So again, the reason why I do this is because it makes it a lot quicker to do that. So you can see like here executed in 4 milliseconds, 3 milliseconds, 3 milliseconds. If I added like an extra, like, let's just kind of show you what would happen if I start adding some more dimensions. Oops, press the wrong button. Okay, and let's just add on the same parts here. Or you know what I could do? Let's use some Python. Let's make it 100 dimensions, or I guess 300 dimensions. Okay, so you can see here, and it's gonna be the same differences and stuff like that, but you can see it's really big. But now I can go ahead and run this part. You see still 4 milliseconds, 4 milliseconds, and then 4 milliseconds. In this case, 700, which makes sense. You just have more steps. So you can see like even this part right here, I could probably put it into like that large, right? That's the same number. And you can see it's still very quick. You know, it's 5 milliseconds, so that's a little bit slower than normal, but still not bad, right? Still very, very quick. Compared to a for loop. For loop, you'd have to go through 100,000 times subtracting each single one. If you can see now, if I do like 10 million times, and this is just me hammering in the point that's like, hey, you can do this and like actually do this stuff. So, oh, I missed 0. So you can see this takes a little bit longer now because actually defining each of those parts is doing this multiply part. But then once I have this part, you'll see that it's much quicker. See, you still got quite a bit of time, but 170 milliseconds is much faster compared to trying to go through, what is this, 10 million? Yeah, so if you did a for loop, that would be extremely slow. So just know that that's why we can do this vectorization. Okay, so cool. Any questions on Manhattan distance, on how this works? This one, I think this is like if you told like a first grader, like how far is something? A first grader would probably like, you know, do a little walk and say, okay, it's 20 steps this way and then like 30 steps this way. Next part is probably what you're most familiar with, Euclidean distance. So once you learn Pythagorean theorem, also called the Pythagorean distance, it's the same idea. Basically, it's like, hey, like we want that Pythagorean, using the Pythagorean theorem, x squared or a squared plus b squared equals c squared, right? Where our distance a squared is this x1 minus x2, though you can just switch that around, doesn't matter. And then our b squared would be y1 minus y2 squared. Okay, and we get this c squared here. Pretty straightforward. Again, you can see that this distance right here, this is actually the Pythagorean or Euclidean distance. Usually you'll hear it mentioned as Euclidean distance. And it's basically just like, well, I'm sorry, this is one way we could have done. This is right here is the Euclidean distance, that green line. So I'm not gonna harp on that too much, but the distance formula, it's pretty straightforward. It turns out you can actually generalize this to multiple dimensions. So usually Pythagorean theorem, a squared plus b squared equals c squared, is usually defined as like only in 2 dimensions, but you can actually extend this out to any dimensions you want. So what basically that ends up looking like is that we have the different directions. So like if I had, I'm gonna just write it down, just kind of show you guys, is that basically all you have to do is sum up and say, all right, what's the change in x squared plus the change in y squared? Okay, and then we had 3 dimensions. Oh, plus the square root of, I'm sorry, plus the square of z squared. Okay, and then plus this, the change in, let's say, some dimension w squared. Okay, and then you just take the square root of that whole thing. That's what this formula really is. So it's just basically looking at every single dimension and taking that square root after you sum it. So again, we can use NumPy to do this. I'll do this very quickly. So we have the same vectors for a and b, right? And I say a minus b, okay? I can square it with just multiplying it together. I could probably have done that a little differently, but that's fine. And remember, I can do this part right here, and this why I can do this is because NumPy defaults the arrays where I'll do the first element times the first element, the second element times the second element. So that basically allows me to do a square of that difference. But again, this is where broadcasting and knowing how NumPy allows you to multiply numbers together. So again, you can see here 1 squared, 4 squared, 2 squared, 1, 16, 4. And then I just sum them all together, which is 21. And then at the very end, I have to take the square root, right? So I take the square root and I get about 4.58. So you can see that even though these are the same points for the Euclidean distance, you'll see that it was smaller than what we got. Well, if you remember, we got 7 over here when we used just, 3 dimensions. But it's much smaller. Well, it's not much, well, I don't know. It's smaller than the Manhattan distance, okay? And Euclidean distance is usually what we'll use for most of KNearest Neighbors. I'll put a little caveat on that, but just know that this is generally what we use. And that's usually what we think of like when we say something's near. Now we can actually generalize this formula here, this guy right here, to something called the Minkowski distance. And basically, if you think about this, all we did here was raise it to the power of 2 and took a square root. So the Minkowski distance is basically can be used in a normed vector space, which essentially all you really have to know about a normed vector space is that we can use different vectors to span vector space. And essentially it's nothing that's too weird, basically. There's like, for example, we don't have, what's it called? A hyperbolic geometry. We can just basically use like the classic like increase, what's it called? Like 1 unit is 1 unit over. And so just know that almost everything that we'll do is probably a normed vector space. If you're curious, I would look this up. I think the curriculum actually points to a resource that kind of this explains this a little bit more, but we're not going to worry about that since almost every vector space we're going to use in data science itself, because it's linear algebra, we're going to have a normed vector space anyway. Okay. So this is the actual formula, and this is what I mean by generalized. So you can see here, take the absolute value here, raise to the power of c, and then basically take the cth root, or 1 over c. So remember the square root is just 1 over 2, right, to that power. And note that I have this absolute value here. That way, in case, for example, if the power is odd, for example, like to the power of 3 or to the power of 1, we will get a positive number every time. It makes sense to have a distance always positive. You can never have like something like negative meters away from you unless you're talking about a coordinate system. But we're talking about beyond a coordinate system. So just know that this right here is the generalized form, and we can put whatever we want for c. And there's some reasons why you might want to do this, depending on like if you want to like really punish parts that are far away. But just know that this is kind of like this is the way we generalize our distance formula for the most part. Okay. And so in this case, you can see I can define like a function here where AB, right? And I just take look at absolute value, then take it to the power of c, and then sum it all together, and then take the cth root of it, 1 over c. Okay, and I'll make my new function Minkowski. And look at that, that's a really short line. I could have wrote this like more like compact, but even writing it like in different parts, I have only like 5 lines of code in my function. So pretty simple. So you can see here, if I do for my vectors again, AB, and I want to do something like, in this case, I put the default is c equals 2. So I'll just put like 2 just to make it clear. You can see we get the Euclidean distance, and we do 1, we should get 7. Okay, and we can actually get into different Minkowski formula. So for example, if I do it to the power of 5, so the power of 5 on 5, and you can see it goes down. In fact, if I keep going down, you'll see that it decreases smaller and smaller. I think, but at a certain point, it just gets to the smallest point possible, right? So you can see it goes basically to 1 here. So I'm gonna play around. Again, usually you won't just like put these random numbers in here. Usually we use the Euclidean distance, but sometimes there are points, depending on the data, where you might want to use the Minkowski. Okay, and that just depends on the domain. All right. So any questions about any of this distance formulas?
Why would you use a Minkowski thing? Just to punish more distant values?
So it depends on how you want to measure what something is near. I'm trying to think of a good situation of when you would use Minkowski. I actually wonder if the curriculum talks about it. But the big reason is just, well, one can just be efficiency, but in this case, it's not that different. You might, for example, how do I say this? Is that Euclidean distance makes sense when you're like, okay, like it's just an absolute value of how far something is away. But if there is something about the data that says, hey, like we want to consider points that are like, that are actually far away, like, or like, farther away. We want to consider those at a different scaling. Again, it depends on I think it depends more on the situation than the calculation reason. Essentially, I'm thinking, again, for the most part, usually it's Euclidean, but depending on how the data has traditionally been done and how like that field uses, you might use the Minkowski to basically make it consistent with everything. But yeah, this is kind of weird just because usually for KNearest Neighbors, we just use the Euclidean distance. And then we adjust with something called K. So yeah, I don't have a good answer for you, Matt. I'm sorry. But
okay.
Probably use some more research on that. Okay. So cool. Any other questions you guys have? All right, cool. So we'll go into KNearest Neighbors, or KNN. Okay. And basically, this is our first, like, is it our first? Nah, it's not our first. I keep saying our first, but like, I feel like this one's like, oh, here's some real machine learning. Naive Bayes is, I mean, even regression, linear regression is a machine learning algorithm. But naive Bayes is kind of like our first like classification algorithm. KNearest Neighbors is kind of like, you can explain this in like 30 seconds kind of deal. So I'll explain this in a second, but just know it's a classification algorithm. So in machine learning, we actually have basically the whole point of machine learning usually ends up being, hey, let's classify things. With regression analysis, or sorry, linear regression, we're actually trying to predict, kind of like on a scale. You can actually use K-nearest neighbors to do regression. The curriculum doesn't really talk about that, and there are resources in that. I would say, you can check it out to see how it's done. It's a little interesting, but uses the same algorithm and then approaches that to say, hey, how can I make it a regression? The main thing is mostly used for classification. And when we do classification, basically we're just saying, like, all right, here's a bunch of information, and we want to say who belongs with what group, okay? And note that this is a supervised learning. So we're going to discover two different types of machine learning in our course. Unsupervised learning and supervised learning. And supervised learning basically says, I know what like from a testing training set, I know what the labels should be. I know what they should be classified as. And unsupervised learning says, I don't know what the labels are. Can you, like, basically you tell the computer, like, you try to figure it out. So what I mean by this is that a supervised learning, you might know, oh, there are cats, there are dogs, there are cows, you basically define ahead of time what a cat is, what a dog is, just the fact that they exist. And unsupervised learning, it says, hey, are these different from each other? So just know that this is a little different. This is our big supervised learning algorithm. We'll look at a similar thing called k-means clustering, and k-means clustering will be an unsupervised learning, but it'll have similar tones to the k-nearest neighbors. Okay. So comes down to, like, what is k-nearest neighbors? So this kind of goes back to when I was talking about, here, let's keep this up. When I was talking about, like, oh, things that are close together are similar. And so, for example, we have like our x-axis, our feature, and our y-axis. And basically all you do is say, all right, we have a bunch of training data. In this case, you can see, like, in this picture right here are red stars and green triangles. And you basically say, okay, like, you label everything essentially. Like, you can think of it like on like some kind of space, like, let's say two-dimensional space. You say, okay, these are all red, these are all green. And then you say, okay, cool. Those are my groupings. And then you just throw in your points. Say, all right, I have this new point. I don't know if it's a green triangle or a red star, but it lands right here on my, like, my space with a bunch of stuff around it. And you say, okay, cool. Who's near it? Basically, like, who's really near this point right here? And basically you try to figure out, like, okay, like, who's near it? And then you say, all right, depending on who is nearest and how many are near them, you say, okay, well, it's closer to be a green triangle, or it's closer to be a red star. So, like, if I had, for example, a point, I'll draw it in color like this. If I had a point like right here, okay, you probably say, like, if I said, okay, what kind of point is this? I could probably tell, like, a third grader, and they'd be like, oh, that's probably a star, right? It's like, okay, yeah. If I drew a point right here, you're like, okay, cool. Like, what point is this? Oh, that's probably a triangle. I'm like, all right, cool. And then you have one in the middle right here. Then it starts going, it could be a star, it could be a triangle, which is which? And in that case, what you do is you have basically, you can think of it like voting. Is this, when we calculate that distance, we're basically saying how much do these nearest neighbors, right? These nearest neighbors over here, how much does their vote count? And if they're really, really close, then their vote should count a lot, right? If they're further away, you would actually say, okay, you have less of a vote. And that's kind of what the distance is. So again, this is why like we tend to use Euclidean, because that seems to make the most sense. But you can use the Minkowski. So you can think of distance as in some ways like a way to vote, saying like who's, what you're gonna do. So for example, like here, you can see it's like, okay, well, there's one that's really close here. There's another one that's farther away, and there's another one here. Well, this means that it's gonna be voted more for a triangle because this one's closer. Even if I got rid of this guy right here, you'd see, oh, that's a triangle here. But if you had something like a bunch of squares like this, even though they're farther away, it might, depending on how you define the distance, it might make sense like, oh, this should still be a blue square because there's more near neighbors. Maybe this is just an outlier. Maybe like you can see like how far away these triangles are over here. So just kind of like know that the distance essentially it's its voting factor. Okay, does that make sense to everyone? Cool.
Yeah.
All right, cool. Yeah, it's a pretty simple one to explain. Like, again, basically just say, hey, where's everything at? You throw your point in there and say, all right, who's near you? And whoever's near you, that's the value. Of course, it gets more formal. So a couple things to know about k-means. One is that it's a lazy learning, which actually is a good thing. Well, it depends how you say this. But lazy learning means that we don't have to do a training phase. Basically, when you load the data in, that is the training phase. You basically, all right, this is my data. And you're like, cool. You don't have to do anything special. Right? So it's kind of nice to be able to do that. It's also easy to interpret. I think it makes intuitive sense. If something is near something, it's most likely like the things that it's near. Okay, so it's kind of quickly to be able to see it. And plus you can do a very quick visual on how that looks like. The disadvantages, there's a few of them on here. And this is one reason why it's kind of like considered, I think it's one of the first ones we kind of like introduce a lot of like machine learning algorithms because it's like really simple, but it has a few disadvantages of why we don't use it. It has to be kept in memory. So remember, it's a lazy learning. Basically means you put all the data, you're like, all right, here's all the data. All right, let's go ahead and figure it out. Well, the problem is that in order to actually test out for that, let's say that questionable point, we have to look at all the data and say, all right, like who's near you? And you have to look at each part and basically figure out, like we can visually look at that, but the computer has to actually calculate like, all right, where are you in space? And there's some efficiencies you can do, but in the end, basically comes down to the fact that you have to know what all the data is. So K-nearest neighbors is best with small data with few features. Basically, if we don't have many features, or if we have few features, we don't have to worry about so many dimensions. We'll talk about that in a second, Recursive dimensionality, but also small data. It's like we don't have to put it all in memory. Okay, it's also not robust. It doesn't generalize well. And what I mean by that is that if I only have like these points right here, and then I have new like triangles over here, if I put in new data points in here, it'll still remember the old training data. And it means it just can't really generalize well on like trying to adjust that formula. You would have to put in a lot more data in order to adjust. So like, for example, if we have like older values and stuff like that, maybe you want to basically bump up some of those newer values. And at that point, it starts getting more complicated and more computationally inefficient, which we'll talk about is already an issue with KNN. So like there's other algorithms that do much better basically learning the information and generalizing better. Okay. So this kind of comes down to soft boundaries are troublesome. We'll talk about how you can make boundaries a little bit with using the K, but the main thing I want to point out here is that it's not clear where the boundaries should be, especially mathematically. It's like, well, okay, there should be some boundary that kind of cuts this off, but where exactly that fits is not always very clear. And it's kind of like a guess of saying, well, what looks well, and then ends up being like, you know, it's like, well, we can do some error analysis and stuff. So soft boundaries can be kind of an issue because we don't have data in those boundary points. And then recursive dimensionality, which I kind of alluded to, is that if we have a lot of features, it just turns out that the data tends to be more sparse, which means it's less certain. Like basically, it's kind of like if you have a big like empty space over here. If I have a data point that's over here in this corner, I don't really understand if there's supposed to be points over here. And when you get into higher dimensions, more features, you end up having more ability to be very sparse. This is something I could talk about a long time because I think it's really interesting. But basically it comes down to the fact that like if you have more dimensions, there's just essentially more degrees of freedom for you to move around in. That's the way I like to think about it. And just means that there's just points that are just not clear or close together. Okay, so one way we can do this, we'll talk about this next week, I think next week, but definitely in this mod, PCA, basically that allows us to do projections to basically take something that's a higher dimensional case and put it into a smaller dimension, and that helps us with the calculation. We lose some information when we do this projection, but PCA kind of helps us try to minimize at least, how much information we're losing. And then if we're using high dimensions, there is something that the curriculum doesn't talk about, but you can use something called cosine similarity. And basically it's just, it's a way to essentially say how close something is, but instead of measuring distance, you instead measure basically how far away is that angle, those vectors from each other. So something to look up there, but for the most part, you'll probably use Euclidean distance for KNearest Neighbors. But these are a couple ways you could try to solve for KNN. It's a quick, easy one. It's useful for a lot of businesses. Business data, if you don't have a lot of data and a lot of features, you can do a KNN pretty quickly. Okay, so those are advantages, disadvantages. So one thing, like, kind of the curriculum kind of teases, like, hey, it's KNearest Neighbors. What the hell is this K, right? And K basically says how many nearest neighbors. So we have to figure out, like, well, how many neighbors do we consider? Do we consider just 3 neighbors? Do we consider 5 neighbors? Do we consider 50 neighbors? Like, how many neighbors do we consider before we cut it off, right? We don't consider every neighbor. And the reason why is because, well, it's computationally inefficient. Is that it basically, if you had like 1,000 data points, for every single new data, you have to recalculate the distance for 1,000 data points. So we're like, okay, like that might not be the best too. And plus, do we really want something that's really far away to really matter? It's like, well, no, we probably don't really care about it that much. We want to talk about the stuff that's very close together. So we can actually determine K. So you can see here, like, for example, if we had just one, what's it called? One nearest neighbor. Okay, you say, oh, just use the closest one. If we had 3 nearest neighbors, it'd expand out until we hit 3 of them, okay? And then as we get further and further out, the way we can kind of look at this, like say, well, what's the best one, is that we'll see like underfitting versus overfitting. This is the classic example. And basically trying to figure out like, okay, like this, for example, is not getting those extra information. You can definitely see it's miscategorizing some of this information. If we have a better fit right here, you can see there's much better of a curve. And this is from the curriculum, just to kind of point this out so you see this this picture again. But you can see right here, it's like, okay, like we have a much better prediction. And then here, we do have a better prediction here, but it's overfitting. And so basically what happens is that if you have not many nearest neighbors determining, if you have a small K, you'll tend to get underfitting. If you have a larger K, you'll tend to get overfitting, okay? So just kind of know that's kind of like what we're talking about. So just to let you know, you can use an elbow plot. So an elbow plot basically, and the curriculum shows this, so I'm not gonna go into full details of how to implement it, but you can think of it, say, okay, like let's say how big is our K? And this is our error. Okay, it's like our validation error. And what you'll see is like, okay, when we start off with a very low number K, you'll get a lot of errors. And then as we get closer and closer, bigger K, you'll see it smaller and smaller. And basically what it comes down to is like, well, you'll get better error. You want to find this elbow. Like, where is the sweet point right here? And that would be part of your validation analysis. So one way you can do that is doing an elbow plot to figure out, saying, hey, when is K good? And basically it comes down to just try a bunch of Ks out until it goes through. And usually it ranges from about 1 to 19 is usually a pretty good set number. And that way you're not also testing 50. Usually you don't find that much difference when you test that many more points. Okay. So any questions about this, about underfitting, overfitting, finding K?
Nope.
Okay, cool. So I'll move on to actually implementing it, which is always fun. And know that in the curriculum, there is a lab to do K-nearest neighbors by hand, by scratch. And that's good. I think it's definitely go through this, but know that most of the time we're not doing it by hand because we have packages that are pretty smart and actually do a pretty good job figuring it out. So this is what I'm going to show you. So first thing I'm going to do is just make some fake, I'm going to load some data from Sklearn. Sklearn is a pretty popular package to do a lot of machine learning. It's an open source tool. It's just know that it's kind of like the go-to for a lot of people. Okay, so I'm going to go ahead and run this guy. Oops, let's go ahead and plot you out. There you go. So you can see here, I have some data called the iris data. It doesn't really matter what it is. Basically, it's about flowers. But no, I just look at 3 different features. Okay, I think there's 5 features, numeric features. There's only about, if I remember right, I think I want to say there's like 30 data points, but like I think that's more than that. But there's not that many data points in here, so it's a good one for KNN. So just know that I just did a scatter plot. You don't really care about what this stuff is, but basically you can see I colored it by what their target is. So you can see, okay, these are all like the gray ones, these are the orange ones, and these are the red ones all the way up here. So you can see there's some mixing down here, but the red ones are pretty clearly red, okay? So now we can actually implement KNN, right? And so we can actually use Sklearn, and there's a few neighbors classifiers, but we're gonna use the KNearest Neighbors classifier, okay? And in this case, I'm gonna define, there's a few metrics you can have in here, like you'll see right here in the documentation, how you can do the weights and everything like that. You can use a Minkowski metric and stuff like that. But the main thing I'm gonna do is say, okay, 3 neighbors. So that means basically, I'm gonna start off saying, all right, there's 3 different neighbors and the metric is Euclidean, okay? So that way we can just do basically Euclidean distance. So this fitting function basically just loads the data right here into memory. So now it's like, okay, cool, I'll use that data. Okay, that's all set and ready to go. So now here's my prediction points. So you can see here, I have 737, 847. Very quickly, just like, this is the X, this is the first element, the second element, the third element. We'll plot these out to see it better. But if I go ahead and run this now, it's like, okay, cool. I'm gonna take all these points and each point for neighbor predicts, nay.predict, it'll say, okay, is it a 0, 1, or 2? Basically, it's a gray, orange, or red. So I run this now, and you can see here, it says, okay, for each of these points, it's gonna be, oh, it's the second color, the first color, or sorry, the third color, the second color, and then like the second color. So first, second, third, right? Basically, it's just saying, okay, what things are points. So this is kind of hard to tell exactly. You could, for example, kind of like plot this point and say, all right, does that make sense? But we're just gonna do it all together in a second. And then this last one right here, this one, this prediction.probability, it's kind of nice because sometimes it makes sense like, oh, it's definitely this one, or it's pretty certain it's this color, but sometimes it's not sure. So you can see as I went for each point and said, okay, it classified it as a 2, and this is the probabilities of how likely it is this value. So for example, it's like, oh, 0 probability that it's a 0, 0 probability that it's a 1, almost 100% for it being 2. And you can see here, most of them, for example, are pretty much like pretty certain, but a couple of these ones down here, it's like maybe 67% certain that it's a 1, with 33% likely that it's a 2. So it's not quite sure exactly what it should be, but it's got like, okay, well, I'm pretty sure it's this one. Okay, and you can look at this formula for how it's predicted, but I won't go into that. Okay, so now let's go ahead and plot out our prediction points, and I color them. I make the prediction points bigger so you can see them more easily, and I also color them for what they're predicted to be. So you can see here is that this should be the same data. Okay, and you can see here, these are my prediction points, and you see that's a pretty good job. Now you can notice the one up here, this orange one, that's one of those ones that's like 67%. It's really far away. It's not really sure. It's like, well, it might be orange, it might be red, depending on how this calculated. It's a little hard to see in 3 dimensions on a 2-dimensional space like this. If I could turn it, maybe you'd be easy to see it, but maybe these values had a little more factor. This red right here might have been a little bit of contributing, but it's not 100% really sure how this should be classified. Clearly this should be red because it's way up above, but know that just kind of like, that's how it's graphed out. Cool. All right, any questions you guys have? All right, cool. So that kind of talks about K-nearest neighbors. It's one of the simpler algorithms. I would strongly suggest like reading the documentation from Sklearn about K-nearest neighbors. There's a whole bunch of stuff because it's one of the simplest ones to kind of explain. And then the curriculum obviously talks a little more about that. Okay.